Hi, I'm Martin. This is joint work with Stefan, and I'll present our paper, A Dictionary Parsing Translation of Featherweight Go. The Go programming language, it's a recent language that is pretty popular. That is partly also due because it has syntax similar to C, which makes it a pretty accessible language. Go is also a powerful language because in Go you find many well-established concepts. So you find garbage collection, higher order functions, a simple form of type inference, building concurrency in style of communicating sequential processes. What we're going to look at today is method overloading and interfaces. I should say that Go does not support class declarations as found in C++ and Java, but it comes with a specific form of method overloading and interfaces. So that fragment of Go that covers method overloading and interfaces is referred to as Featherweight Go, and then has been specified in a recent paper. Now, the conditions or the restrictions imposed on method overloading in Go are such that an overloaded method call can be resolved by only knowing the type of the object on which the method operates. That means the arguments do not matter. No? You only need to query the type of the objects to uniquely identify the definition we require here. So in the Featherweight Go paper, such a runtime method lookup semantic has been specified. So it's a simple semantics, but it's not very efficient. So probably that's not what you want to use to build a compiler, because you would need to query the runtime types all the time. In the context of type classes, so type classes are another form of overloading, we have an efficient translation scheme, and that's called the dictionary translation scheme. So the idea of that translation scheme is to have a source to target translation. So we analyze the source language, the source program, and then we generate some target programs. So here's a classic example that uses the equality type class. In Haskell, type classes are implicit, but if you see a type class, here the equality type class, we know that we have available an equality method. Yeah? And the idea of the dictionary translation is to make these implicit arguments explicit. So we explicitly now insert dictionaries in the program, and in these dictionaries, we find now the specific equality definitions. Applied to Go, or the good thing is actually, it seems that the dictionary translation also applies to Go. What we can do now is actually, we can translate the object to a pair of values. No? So clearly we need the object value. So we need the object value, but in addition to the object value, we find a dictionary. And in that dictionary, we find the corresponding method definitions that match the value. Now, when we have a overload method call, it's not pretty easy to resolve that method call, because all what we need to do is we need to access the definition of M in the dictionary. So this seems to be implemented by the Go compiler, but nobody has formalized it so far. No? And here we come. In our work, what we'll do, we formalize this dictionary parsing translation for Featherweight Go. So it's a source to target translation, and as we are interested in the theory, we also want to know and establish that the translation is correct. And we establish semantic correctness by showing equivalence of the source program to the target program. The target programs, they are formed using a very simple target language. It's a functional language where we only find first order functions and data constructors and pattern matching. So in the remainder of this talk, I'll give you the highlights of the idea behind the dictionary translation scheme via a bunch of examples. To be able to read and parse the examples, well, we need to know a little bit about something about the Go syntax. It's very close to C, but in Go, we're having a keyword to introduce functions and methods, the func keyword, the keyword. In Go, when we have variable declarations, the order of the names and the types are switched. So we first have the variable name, and then we have the type. And in Go, when we have a return type, it comes after the parameters. And that's pretty much all you need to know to be able to read and to parse the coming examples. So our first example, we deal with an overloaded method to compute the area of geometric objects. In Go, we find structures. So we have here a rectangle structure and a square structure. And as I said, the order of variable declarations or field entries the order is switched. So we, for instance, have first the field name length followed by its type. When we have method definitions, we can use the func keyword to introduce method definitions. But the difference to function definitions are that we first have the object on which the method operates. In Go speak, we often refer to the object as the receiver. And the important condition in Go is that the name of the method and the receiver uniquely identify the method definition. I mean, the parameters of the method, they do not matter. In our case, computing the area is pretty simple. For a rectangle, we simply multiply the length with the width. And in case of a square, we simply multiply the length with itself. Translating such a language is not too difficult. What we'll do is, in the translation, we represent structured data using data constructor. We're assuming data constructors labeled K, indexed by the name of the structure. So we have here a rectangle, and we effectively tag the values of a rectangle, where for convenience, we assume that we also have pairs in the target language. Now, when we translate a method definition, we need to guarantee that in the target language, the function names, the resulting target function names, they are unique. And we can do that because we know that the method name and the receiver on which the method operates uniquely identify the definition. And here simply I can create here a unique name for the definition of the area method for rectangles. Because we've translated structures to data constructors, while we're using pattern matching to access the individual components of a structure. Okay. Such plain form of method overloading is actually rather limited. And here's a simple example. We want to sum up the area of two geometric objects. So we have here the case of a rectangle, and we have the case here of a square, because we're not allowed to overload a method based on its parameters. What we need to do is we need to define our functions that cover all the cases. So we need to really enumerate all the cases. We need to enumerate the case that we have a rectangle and a square. We have to cover the case that we have a rectangle and so forth. This is pretty tedious. And of course, we see that the function bodies, they're always the same. So what is really required here is a generic representation for these geometric objects. And this is supported by Go. Go supports interfaces. An interface is a collection of methods that share the same receiver. Remember, the receiver is just another name for the object. And here, in our case, we simply introduce the shape interface that comes with the area method. So the receivers are always implicit here. And as we've seen, square and rectangle, they both implement the area method. So we say they both implement shape. Okay, now how can we use these interfaces to write generic code? Well, interfaces are types. So I have here now the case of the sum area function, okay, which takes in two parameters, x and y, and they're both of type shape. And because any value of type shape comes with an area method, that's why on x and y we can call the area method, and we simply add up their values. So how do we now translate such an extended language? And how does the dictionary translation apply here? So here again, a brief summary of our running example. We have here the shape interface, and we do know rectangle and square, they both implement the shape interface. That's why we know, for instance, that particular rectangle value and that particular square value, they also are interface values. And the idea of the dictionary translation applied to Go is now that these interface values, they consist of a pair, the actual value and the dictionary that holds the corresponding method definitions that match this value. So in our case, we have now a rectangle value, which is also an interface value. And in the translation to the interface value, well, we again use a tagged representation. We're using our data constructor. We have a pair, and the first component of the pair is the actual underlying value, just the rectangle. And the second component is a dictionary. So of course, in our case, the dictionary is always consisting of a single method because I'm using a very simple example. And here in the dictionary is nothing else than the instance of the area method for rectangles, and similar for square. Okay, good. Now, when we translate method definitions, we simply assume that in the translation, we pattern match over the interface values. So because we know value of type shape in the source will be translated to an interface value consisting of a pair. So we simply pattern match, and we can now access the underlying value and the corresponding method definition. And then we simply call the corresponding method definition with that specific value. So we, in this case, again, we're using pattern matching to access the concrete value and the corresponding method definition. And this leads then to a pretty efficient translation scheme that is a variant of the dictionary translation scheme. Now, I should say that the translation is actually type directed. So that means based on the types and the typing of the program, we build the target terms, and the case we've seen so far is actually structural subtyping. So we have here that rectangle implements a shape, and we have never specified in the program any subtype relation. That's why it's a structural subtype relation, because we know that rectangle implements the area method. And how does this work now? The type-directed translation. Well, here we have an example where, for instance, we call the sum area function, and we do know the sum area function expects interface values, but here we have actually a rectangle. And we do know a rectangle is in a structural subtype relation with shape, and so we are introducing here interface value constructions. We are turning the rectangle into an interface value. And this is now all done type directed. Okay, so this is the gist behind the dictionary translation applied to Featherweight Go. All the details you find in our paper. In case of Go, there's not only structural subtyping, but also type assertions. So of course, a few more tricky cases. Please read the paper. You find it written up in the paper. In our target language is untyped. It's a very simple language. It's just untyped for convenience. We could have come up with a typed target language, but that would have been require a bit more work. The semantic correctness, it's an obvious result. So it's kind of obvious if you look at it. Oh yeah, sure. The target is semantically equivalent to the source, but it's tricky to prove. So many things sometimes they are obvious, but the proof is really hard. And in our proof, we are using step index logical relations. All the details you find in the paper. Thanks.